posted in the file section a sheet. I'll try and bring it Thursday. I didn't bring it today, but it has a lot of statements like for the exam. You need to know the power rule. You need to know how to use this. You need to know that. And it's extremely unlikely that something would show up on the exam that doesn't fit. Those categories. So that should give you a good sense of what you need to know. Yes?
Can you start off the exam cover all the units before today? Or would it cover things that you're studying?
It certainly doesn't cover anything from here on, yeah. Yeah, up till wherever we were Thursday. And I'll be clear about that on the next midterm also. There's some physics principle here. Sound travels slower in colder weather. Students also, I guess. Okay. Some thoughts about this section over the last few days, so I'm going to try and present it a little better than I have in the past. This is a starting point where I'm faced with derivative of the actual log of x. So how would we figure out what that might be? Well, we can try the formula. We can try the formula for derivative. And what would we get here? We get x plus h, x over h. And we look at that and think, what can we do with that? Well, we have our laws of log, so say limit of x plus h over x. H. And we'd stare at that for a little while and go, well, wait a minute. Clearly, the natural log of x plus h over x, as h goes to 0, x goes to x over x, which is 1. The log of 1 is 0, and this goes to 0. So that doesn't really get us anywhere. And it's a little confounding because we know the derivative of e to the x, that's just e to the x, that's its inverse. So you've seen that there might be some way to find this a little more directly and maybe give us some insight into how we find derivatives of inverse functions knowing the function. So I'm going to erase this just because I really don't, we're not going to need this. So we're going to start with something really simple and obvious. Let's take the function f of x equals 3x. This is working, but I don't like it. Then we want to tell me what the inverse function of this is? That's right. I'm just going to write it this way. All right. Let's take a look at what that looks like. We have there's our function 3 to 1. There's our inverse, kind of 1 to 3. And as mentioned a few times before, with an inverse function, you graph them. They're kind of reflections over this line y equals x. And thinking about this as delta y over delta x, you see that what we really have here, I'm using these numbers, right? This is 3 over 1 is delta x over delta y. 3 is not x, delta x, and 1 is not delta y, but if you were to kind of swing this around and make this the y-axis and this the x-axis, that would be true. So we have this kind of obvious, interesting that, the derivative of this function, in the case where it's a constant, is just 1 over derivative of f of x. Ibby is not here, is she? Okay, she was going to come first day today. We'll see her yet. So, I mean, that's true for this linear function. It's an interesting proposition we got there. Wouldn't it be nice if it were true in general? Yes, it would be true in general. We're not going to prove it. I am, however, going to try and make it seem plausible. This is the case. So to do that, I'm going to look at this is just kind of a representative function. I'm going to draw a parabola. This happens to be f of x equals x squared. And I'm going to think again about how we find the derivative of this. We have some point C, and I'm sorry. Yeah, well, I'm just going to call it x. It's any old point. And we have some other point that's h away, so it's x plus h. And we have the function at f of x and x plus h. And we draw a line here. Pink. Maybe a good color. And then we move h, and we find a limit, and we end up with a tangent. Well, thinking about this idea that we're reflecting to get the inverse along the line y equals x, well, we end up with an inverse function, and reflecting these points here, do the best I can, we again, see that we have 2 points now, and as h decreases, we get a tangent. So for f prime of x, of course, we have x plus h minus f of x. For h, the limit is h approaches 0. But what we're doing here, if we do it right, for the inverse function, all the coordinates are switched, the x coordinates and the y coordinates. So for the inverse function, it's just going to be the reciprocal. In other words, each of these points on the inverse function, if I kind of doing it parallel to this, just switch the coordinates. Well, that switches delta y and delta x. And this clearly, this is the limit h approaches 0 of 1 over f of x plus h minus f of x over h. But here we have derivative of f of x. So again, this is not a proof. This is just trying to give you a feel for why this is true. Every point on here is a tangent. The associated point on here, there's a tangent. But the slope is its reciprocal, just like it is in the case of a linear. You kind of draw a direct comparison. Here, the derivative is very easy because you always have the same slope along the line. Here, well, you may only have that slope at a certain point, but on the inverse function, it's going to again be the reciprocal slope, the tangent, the reciprocal slope. Okay, that's the basic idea. Does anyone have any question about this? Yes, George?
On the graph of x squared, it looks like the inverse derivative, it looks like they're going to be parallel. That's the middle, the derivative.
Oh, only if my drawing is bad. Here, let me.
So an inverse derivative, there's no.
That's even worse. This is a curve.
Could they be parallel?
Hmm?
Could they be parallel?
Well, if the function just happens to have, at a point, has the derivative of 1, then they will be parallel. Right? Because the reciprocal of 1 is 1. But otherwise, no. I mean, you might want to think about what goes on at 0, right? Well, y equals x squared at 0 is going to have a tangent that has slope 0. Square root of x coming down this way, he's going to have a tangent which is vertical. He's infinite slope. So it's just, in this particular area, they're kind of converging, and then they match, and then they, way out here, square root of x is going to look like this, and way up here, the x squared is going to look like that. So they're not going to intersect. Leave it to your good judgment to what needs to be done here. Is that better? Okay. All right, so we have this formula here. Let's see what we can do with that. We're going to sneak up on that problem about the law, the natural law here. So I think it's already clear if f of x is just some linear function, ax, well, the inverse function is 1 over ax. We know the derivative of f of x is a, and 1 over derivative of f of x will be 1 over a, which is exactly what the power rule tells you about the derivative of the, inverse derivative is 1 over a. Okay, well that was that first obvious trivial example. Let's look at x squared. Of x equals, okay, so you're going to find when looking at these, it's best to do this in terms, since, the inverse is switching the x and the y coordinates, we're just going to write this way. I still mean the function, but y equals x squared. And because I'm going to need it later, I'm going to write x equals square root of y. So derivative of y is, of course, 2x. And 1 over the derivative of y is 1 over 2x. So x is the square root of y. 1 over 2 square root of y. So if we want to look at the inverse function, write this y inverse, well, I don't want to write it that way, do I? I guess I do. I want to write y inverse in terms of x. I have to switch the variables. So that would be 1 over 2 square root of x. Well, that's exactly what the power rule tells us. We look at y equals square root of x, or x to the 1/2. Derivative from the power rule is 1/2 x to the 1 minus a half, or negative 1/2, which is 1 over 2 square root of x. That's what we expected. All right, so we haven't learned anything new yet. All right, we've just seen that this formula here. Derivative of the inverse is 1 over derivative of the function. We see that this works for a linear function and for square root functions. Let's give it a try for the log. Yes?
So once we find the derivative, we can also find the inverse after that, right? Essentially. Like,
If we have a function and its derivative, we then can find the derivative of the inverse function. That's what we're doing. The function we're going to start looking at is e to the x. And we know its derivative is e to the x. We know the inverse and we derivative of this, well, I guess I should write this as y equals. We want to find the derivative of this. So this formula tells us that, I guess I need this here. Our formula tells us that the inverse here, derivative, is 1 over the derivative of y. Okay, but the problem here is we have this in terms of x. We want it in terms of y. Well, we see here x is the log of y. So if I plug that in, 1 over e log of y is just 1 over y. Or writing it the way we would normally write it. Derivative of the log of x is 1 over x. I hope I'm not confusing this. I always have trouble too because we're switching x and y when we go to the inverse. But that's our result. Has anyone seen that before? Derivative of the log of x? A little more one could say about that. Let's start with x squared. And let's look at the derivatives here. So that's 2x. And x, that's 1. 1, that's 0. This is x to the 1, and this is x to the 0. X to the negative 1, what's the derivative of x to the negative 1? 1 over x. Well, the power rule tells me it's negative 1 x to the negative 2, or negative 1 over x squared, and so forth. Negative 2 over x cubed. So if you're going in this direction, okay, we should be able to figure these out. If we're going in the other direction, we're starting with x to the negative something, negative 3. Well, you see if you kind of undo our derivative, we get x squared. Here, if we undo our 1, we get to 2x and x cubed and so forth. But somehow right here at x squared, we get, excuse me, I messed that up. I think I did. Yeah, we can get to x to the negative 1, but when we get to 1 over x and we're trying to undo it, where do we go? You can't use, you can't reverse the power rule here. But it turns out that this function is kind of what's above it. It's good to kind of have a, write this down. This doesn't really fit. X cubed, we get to x squared, we get to x, we get to a constant, and we get to 0, and out of we're out of room here. It's all zeros. But if we say x to the minus 2, we're going in the reverse direction. X to the minus 1, well then we run into the log x. And then there's kind of this, just like there's kind of a break here, there's a break here. I guess you can go back to a constant 1 and x squared. I don't mean these to be, the derivatives, just, there's constants here that are missing. But just what happens with polynomials when you find the derivative is you always get down to 0, and you kind of have to jump in here with 1 over x to go any further. I don't know if that really helps anything. It's just the way I think about it. Right. So that's the big takeaway from today about the inverse derivatives of the inverse functions. You're not going to be responsible for figuring these things out. But I do want you to see where certain derivatives come from. They're going to come out of this function, out of this formula. So let's take something that is probably unfamiliar. That's a nice, satisfying result. Let's look at y equals the sine of x. Well, we know the derivative of the sine of x. What we'd like to know, and I'm going to use the term arc sine because it relieves me of putting yet another superscript up there. Now, I guess I need to say a little bit about the arc sine. The sine function is a periodic function. It goes on forever. But to have an inverse, we have to restrict its domain, because otherwise you wouldn't get a function. So I do a cosine. Try sine. Same comments about it being periodic apply. So you pick a section, it's arbitrary, that will pass the horizontal and vertical, the vertical line test. So when we invert it, we get something that kind of looks like this. Goes between negative pi over 2 and pi over 2. So that's our arc sine function. I've seen some pre-calc books that make a distinction. You kind of have to be really on your toes. And we'll use a capital A to mean not the function, but the inverse relation. Taking this whole function and uprighting it and getting multiple values out of it. And lowercase, they just mean the function inverse arc sine. This of course, also is what you get if you use a calculator. It can only give you one value when you put the arc sine button. All right. So what do we know about this function, or its inverse? I'm sorry, its derivative. Derivative is going to be 1 over the derivative of the function. Well, here again we have that problem that this is in terms of x, and we want it in terms of, we really want it in terms of y. So how do we convert this? Well, first step is to use the Pythagorean identity. Cosine squared plus sine squared equals 1. So the cosine is the square root of 1 minus sine squared. And then we use the fact that we know the sine of x. So this becomes square root of 1 minus y squared. So our conclusion is that derivative of the arc sine of x is 1 over the square root of 1 minus x squared. That's pretty handy. We didn't really have to know anything special about the arc sine, we just had to know about the sine. Yes?
Can you still use that Pythagorean identity if the cosine isn't squared? So like the cosine isn't squared, but we can still use the Pythagorean identity for the sine. Because isn't it cosine squared plus sine squared?
It's a square root. Take the square root.
Oh, you take the square root.
Yeah, it's a good question. Again, I know you might know all these identities, but not like, be facile in juggling them. So let's just go there. So x, cosine of x. Let's write it the right way. Sine squared of x plus cosine squared of x equals 1. Everybody's okay with that, I assume. We have cosine of x here we want to solve for. So cosine squared of x equals 1 minus sine squared of x. And now we find the square root of both sides. Not happy with something. So I know that this could introduce plus or minus here. Well, if you look here in this particular section that we've chosen to define the arc sine, the slope is always positive. If we were to choose another part of this, I don't know. I think you could get a negative out of it. I think this is just, you get a positive as a consequence of the fact that we're limiting the domain of the sine in order to get our inverse function. All right. You can do the same thing with arc cosine of x, and it turns out you get almost the same result, except it is negative. I think it's worth doing one more of these. We'll do the tangent. A little easier and a little more memorable. You know, it's not memorable if you want to remember it. We have y equals the tangent of x, and y prime equals, this is 1, again, we want to commit to memory. You can, if not, you can put it on your notes. Anyone? Yes?
Secant squared.
Secant squared. And because it will come in handy in a minute, tangent squared plus 1 equals secant squared. If you have trouble remembering this, if you kind of write it out, sine of x squared over cosine squared x plus 1 equals 1 over cosine squared. You multiply this through by cosine squared, what do you get? You get sine squared plus cosine squared equals 1. It's just another form of the Pythagorean identity. So, okay, so our inverse function is the arctan of x, and our derivative is going to be 1 over secant squared. But we can see right away that's just going to be 1 over tangent squared. And that means it's 1 over 1 plus y squared. So our derivative, our inverse function of x, is just going to be 1 over x squared. 1 over 1 plus x squared. So now we have just a few more items in our tool bag of finding derivatives. Arc sine, arc cosine, arc tangent, natural log. And I think those are sufficient for now. You don't have to worry about the other functions at this point, the other trig functions. Any questions about this so far? So just so I don't make a mistake, Ramsey, Econ, these are people not here. Z, Rocky, Maya, Natalia, Alexis, and Jose, who's never been here. There's a lot of this stuff. Finding derivatives, quantum mechanics. And I think you've probably already found that anywhere you're weak in your background here, it's going to show up. Trig, logs, exponents. We're gonna next learn another technique. We're not quite done handling how to handle various kinds of derivatives. I think this might be 7. something called logarithmic differentiation. So here we're going to combine a whole bunch of things that we already have learned, but in a new way. As an example of what we're faced with is something like this. Oh. That's not nice. Kind of looks like an exponential function, but it has x as part of the base too. Might seem that, you know, we have a whole new branch of mathematics to explore here. But we don't. Turns out using what we know, there's a straightforward way to get at this. The technique is called logarithmic differentiation. It's used for kind of puzzles like this. We don't have any other way of solving, but it also is useful for just very mundane problems that are hard. So let's first take a look at one of those. Say we have a problem of finding the derivative of x to the 3/4 times the square root of x squared plus 1, 3x plus 2 fifth. What a nightmare. Well, we at least know how we would go about this. I mean, here you have a quotient. So derivative of this times this minus derivative of this times this over this squared. But then we have to find this derivative, which involves a product. And here we're going to use the power rule, but the chain rule, it's awful complicated. It's just rife for human error. But it turns out we have a way to get around all this complication in a problem like this. So the way we do this, we're going to write this as y equals x to the 3/4 x squared plus 1 over 3x plus 2 to the 5th. And our first step is to find the log of both sides. We're going to use the natural log. Clear. And now we're going to find the derivative of both sides using implicit differentiation. Even though we have it explicitly, now we've got log of y on the left here. So derivative of log of y is what? Well, 1 over y times the derivative of y. That's the chain rules coming in. Okay. Before we, before I go to that step, I want to wait and see. Maybe I can simplify this a little using law of logs. Right? It's the log of x to the 3/4 square root of x squared plus 1 minus the log of 3x plus 2 1/5. We'll keep going here. On Blackboard. It's log of x to the 3/4 plus log of the square root of x. Let me write this the way I want to. This is x squared plus 1 to the 1/2 minus, and I have an exponent here. Take that out in front. Log of 3x plus 2. I have an exponent here too. All right, now I'm ready to find the derivative. So again, the derivative here is 1 over y times y prime. And what do we got here? 3/4 the log of x. Oh, we just figured that out, right? It's 1 over x plus 1/2. Okay. Now we're going to use the chain rule here. The log of x squared plus 1 is going to be 1 over x squared plus 1. But we have to use the chain rule, times 2x. Minus 5 times the log of 3x plus 2. Again, it's 1 over 3x plus 2. But I use the chain rule and multiply by the derivative of 3x plus 2, which is 3. Okay, so I have simplifying a little here. 3 over 4x plus, well, my 2's cancel. X over x squared plus 1 minus 15 over 3x plus 2. The only problem is I don't have the derivative of y here. I've got the derivative of y over y. I can solve that. Let's multiply both sides by y. But of course I know what y is. Right? So I get, it's very, it's an ugly result, but we avoided, much of the algebraic manipulation that's prone to error. Okay, that was long and torturous, but you know your you know your rules of logs, and you know implicit differentiation, and you know the chain rule. It's straightforward. And in general, I mean, even if there were some kind of simplification you get by distributive law here, there's no point. I mean, it's a perfectly good solution if you need to find the derivative at a certain point. It's nice and easy to plug something in here. If you want to see what it looks like, pump it into a calculator, Desmos, and see what that function, crazy function looks like. questions about this? It's just a, we're going to do another one, but a simple one. But again, it's really useful when you have, either like a rational function in x like this. It will also work, you might, we could substitute in like 3 cosine of x. It would still simplify things quite a bit. So, all right. I'm going to go over the break to do this next one, but it's pretty simple. Now that you've seen this technique. Okay. So how do we approach this? X to the x, it's kind of like a super exponential. The base gets bigger, the exponent gets bigger. It's just going to, I don't remember what happens at 0. I think I do remember, but I don't want to give it away because I think it's a problem for a later day. But whatever, something happens and then it's going to be going. It's going to just get bigger and bigger. So we write this as y equals x to the x. And before we attempt to find the derivative, we find the log of both sides, which allows us to simplify this into x log of x. Now when we want to try and find the derivative, we're in better shape. We could use the product rule. Well, x times the log of x, x times the derivative of the log of x, that's x times 1 over x, plus the log of x times the derivative of x, which is 1. Well, that's just 1 plus the log of x. Now that's the derivative of the log of y. Well, again, we see that the derivative of the log of y is 1 over y times the derivative. So we can multiply through by y, and we'll get y prime equals x to the x times 1 plus log of x. So not only can we handle this, but it's much easier than we thought it would be. Much easier than trying to evaluate the derivative formula on something like this. Okay. Any questions on that? This is pretty heavy stuff all at once. Big long day here. I guess let's take a break. Didn't know the copy file got moved. Copies tab. Okay. I guess when you just have no life at all, you have time to contemplate the kind of fun things you could do with logarithmic differentiation. So I guess that's what happened to me during break. And I was thinking, what else could you do with this? Well, what if your function was x to the cosine of x? So y equals x cosine of x. Log of y is log of x cosine of x, or cosine of x log of x. Oh, and now we have a nice easy derivative here. cosine times the log, derivative of the log, plus log times, right, y triangle for y, and then to finish up, you just have to multiply back by x cosine of x. Just kind of make something up that looks intimidating. Looks pretty intimidating. Well, I find the log of this, what do I have? I'm going to have cube root of x plus sine of x, log of x. And I have to find the derivative of this. Well, product rule will get me through most of it, I guess. That's something to think about. Log of the log of x. How would I do that? Well, it's the composition of functions, right? I can use the chain rule. So the log of x is going to be 1 over the log of x times the derivative of the log of x. Yeah, you can do that too. So, you know, this is really powerful technique for functions where you have an x in the base and also in the exponent. In this case, it's a function in the base of x. And here, it's a function in the exponent. Now, I've never really gone here before, and I don't want you guys to either. You know, we're really far from the medical facility, and if anyone's head explodes, it's on me. But suppose if you had a function x to the x to the x, I think you'd have to do logarithmic differentiation twice. Okay. The log of this would be x to the x log of x. Then you could find the derivative of that, but you'd end up with an expression for the derivative here, and then you could repeat. That's an item. All right. No, but it's nonsense. This is all very abstract and mechanical. And thank goodness there are clearer minds in the math department than mine who want me to talk about section 8, which is on exponential growth and decay. So, all of you biologists out there, physicists, and other scientists, economists, need to know about exponential functions, exponential growth, a lot of real-world applications. And if you're none of the above, well, I don't know, maybe it'll be fun anyway. What types of phenomenon in the real world do we see obeying these kinds of rules, at least approximately, at certain times? So, populations of, is the most, I can kind of, bacteria, take a couple bacteria and they start getting food so they can eat. And they reproduce at a common rate, constant rate, so they double, triple, they grow exponentially. Animal populations. Well, if you're, I don't know, you would be a conservationist, zoologist, you know, you got the wolves and the deer, and if there's too many deer, the wolves start growing, and the deer start decaying. There's a lot of interesting problems like that. Human population. Ugh. It's been on the political table since at least the 60s. I don't know. There was a guy named Malthus came up with this idea that it was in the 1800s, that in a short period of time we were just going to overwhelm the Earth with population because it was increasing exponentially, and people were going to starve to death because there wouldn't be enough food. But we slowed population growth and increased the rate of food, but we still have this problem that a lot of problems related to our world are related to population. Between water, food, wars get started over territory. All right, I don't want to get too depressing here. So we'll talk about radioactive decay. This is also political, isn't it? You have nuclear reactors, how do you get rid of the waste? Well, just wait. That's that. We'll go into detail on this. And then something that at least, you know, it's get optimistic about. Compound interest. What this means is if you just put a little money away, figure out a way to live long enough, you can be a billionaire. You just have to live long enough. Because money grows exponentially. All right. So we're going to start off with an abstract view of this type of phenomenon. I'm going to write an equation here. Y dx equals k times y, where y is some function, k is some constant, and we're equating the derivative, the rate of growth or decay of this function. K is negative, it's going to be decay, right? It's going to decrease, to the value of the function itself. This function fits into a category called differential equations. A simple one. If you're a physicist, or a biologist, or an engineer, you're definitely going to be interested in differential equations. There's a whole course that doesn't even cover everything. But we're just going to look at a very simple example here. And this doesn't have to be true for all time. But you know what? I left out time. We're going to make y a function of more practical that way. This might be a good model for bacterial growth in its initial phase. Eventually, bacteria run out of food, and then other things happen. Okay, so not all, but a lot of differential equations are solved in the most rudimentary way. It's kind of we call guess and check. Try and think of a function that we think might fit this. And you can recall that we have this function, e to the x, and its derivative, e to the x. Derivative of a function is the function. Well, here we want derivative of a function to be a constant times a function. So we guess that we make y equals some constant we'll call c e to the kt. Maybe that will solve this equation. So we guessed, and now we're going to check. So derivative of y with respect to t is going to be what? K times c e to the kt. That is, the constant just comes out. This is e to the x, except it's constant times the variable. So we use the chain rule, and derivative of kt is k. All right, so we want to set that into ky, k c e to kt up. Well, that's nice. That works. That's a solution. It doesn't guarantee that's the only solution, but in this particular case, it is. All right. Well, we'd like to learn a little bit more about this function. What happens at time 0, starting point? Well, we get c e to the 0. Well, e to the 0 is 1 is c. So that immediately tells you what c represents here. It's just the starting value. If we were growing a population of bacteria, how many bacteria we started with at time 0. Since we know y is equal to c e to the kt, and derivative is equal to kc e to the kt, we can solve here for k. And it's c e to the kt, or y. So k, this constant k here, represents the growth rate at a certain time divided by the value at that time. And we give that a name. It's called the relative growth rate. What we have left is to actually see how to use this in a problem. differentiation. So, first problem we're going to look at is a population problem. It says that in 1950, the world population was, I'm just going to, million. I'm just going to use quantity million. And in 1960, was 2040, that's 3 billion. And we're going to take this as 0, so 1960 would be 10. And we'd like to know what the population will be in 2025, 75 years. I suspect Stewart wrote this like 10, 15 years ago when 2025 was far off. And he thought, that would be exciting. Look into the future. Now we're just looking 3 years away. All right, so how do we solve this? Let's create a function. We're going to use P for population. C e to the kt. Well, we already know how to find C. That's just a starting value. So P of t equals 2560 million e to the kt. And we know from our data that P of 10 is 3040, which is equal to 2560 e to the kt. Well, here t is 10. So we just have k. So we can solve for k. So how do we do that? We're going to divide and then find the natural log. 3040 divided by 2560. The log is 10k, or k is equal to 3040 2560 over 10. Which turns out to be 0.017185. Okay, so now all we have to do is plug in, we have our equation, right? It's P of t equals 2560 e to the 0.01725 t. Yeah, I'm going to see if I can do better. All right, so we have to plug in for t. If you have a calculator, you might want to just try that on your own. I come up with 9289. Whoa. Billion. 9 billion. Now, it seems that's a little bit exaggerated because the current population is 7.7 million. 7.7 billion approximately. Any thoughts on why that is? We're not quite there. scientists. What does that mean? Yes, Lily.
This projection can take into account the decay of some of our resources like land or food or
Got it.
so it
Got it.
was
That's
a
plausible. I hadn't thought of that. I mean, that's, you're thinking of the secondary, why is the why. But the rate, apparently the rate here is exaggerated, right? What does that mean? That means whatever the growth rate was from 1950 to 1960, it slowed a little, which is a good thing. It's not slowing fast enough, but it's a good thing. And your point is right there. Why? Well, I mean, I'm not sure what the cause and effect is. Like, did we just have to stop growing because we didn't have the resources, or did people think, hey, we don't have the resources, we have to stop growing? So, regardless, it's mathematics aside, it's something all of the people in this room will have to deal with, in your lives. You'll see it on the news every day. Not some days. I'll bet almost every day there's something in the news related to this. Okay. Any questions about this problem? This is a population growth problem. I think most of the problems you're gonna see a few more. The math is the same for the most part. It's just the terminology is a little different. I guess we could check off all of these. So I'm going to talk about radioactive decay. Have a ball of uranium-235. It's the bad stuff. And you have so much of it, say a pound. And it's kind of magic, like the atoms in it know when their time to decay is. It's almost, well, it's quantum mechanics and random, but so after a while, you only have half a pound, and the time it takes, half a pound of the radioactive material doesn't just separate itself, unfortunately. This is called a half-life. I don't know if it came from the study of radioactive decay, or they brought it from somewhere else, but we use half-life for other things too. Nothing comes to mind, but I know in non-kind of nuclear physics context, we'll talk about the half-life as something. All right, so here's a problem. You have a kilogram of radium 266. 266 is an isotope, a radioactive isotope, decays. And the information we're given is the half-life is almost 1,600 years, 1,590 years. So, our t variable will, use as years. Wait a minute. Oh. This kilogram is just text. You start with a kilogram. In 1,600 years, you'll have half a kilogram. But for our problem, we're starting with 100 100 milligrams. Not so much. Okay, so the first question is find a formula for the amount left after t years. So our R of t is going to c e to the kt, where k is going to be a negative number because this is a decay. Remember the change in time is related to, the amount by times a constant. Decay is going to be a negative number. Okay, we know at R0, our C is equal to 100 milligrams. So we know C. And we know that after 1,590 years, how much are we going to have after 1,590 years? Half? Okay. That was a 99.999% answer. But I would have loved you if you would have said 50 milligrams. That's 50 milligrams. That's what? 100 times e to the kt. Oh, but we know t is 1590 years. So again, we can solve for k here. Right? So k is going to be equal to what? First I have to divide 100. But to get rid of the e to the k, I have to find the natural log. And since I have k times 1590, I have to divide by 1590. So my k is equal to, oh, the book didn't even just wanted me to write log of a half over 15. I guess you really don't have to know about, if you know the half-life, you don't actually have to know the quantity. All right, so now we have a formula. It says that R of t equals 100 e to the, we have to write down k, log of 1/2 over 1590 t, where t is in years. So that's our formula. Second question, how much is left after 100 years? Okay, R of 100, just plug in, right? E log of 1/2 over 1959 times 100. And again, if you watch your calculator, just find out 64.7 years. I'm sorry, 64.7 milligrams is left. So radium, pretty slow. Final question, how long until we get down to 30 milligrams left? Well, this is just some basic algebra. This is going to be 100 e to the kt, half 1959 t. Now I have to solve for t. Well, again, divide by 100. Find the natural log to get rid of the e to the exponent. And then divide by log of 1/2 over 1959. And that will be our t. That turns out to be 2,762 years. I'm not sure if he's like injecting a little political statement here, you know. Waste products for our nuclear reactors, they last for billions of years. Billions? Millions of years. So we're stuck with them for a long time. And they're not very safe to be around. The last part, I'm hoping, now we're going to look at interest. This is just as important, especially if you're an economist or you're going to go into finance. I hope it's reviewed because this is usually part of a pre-calc class, but compound interest. So, basic compound interest kind of looks like this. Future value in dollars or whatever currency is your present value times 1 plus the interest rate, which I'm used to using I, but apparently it's common to use R for the interest rate, times time. That's if your interest rate is in the same units as your time. So this is like typically a yearly interest rate, and T would be in years. But you might want to compound it more often than that. So, for example, if you compound it quarterly, it would be P times 1 plus R over 4 times 4T. Or daily, P times 1 plus R over 365T. To get to the next stage, we want to do a substitution here. We're going to create a variable m. First I want to write this as P1 plus R over n, nt, where n is the number of divisions we break this unit into. And we're going to define a variable m equals n over r. So this equation becomes P of P times 1 plus 1 over m to the m to the RT. Again, that's our future value. So the next thing we do is we say, well, what happens if we just keep dividing m by larger and larger values? We find the limit as m approaches infinity, p of 1 plus 1 over m t. Well, we can move the, since p is a constant and r and p are constants unrelated to m, we can move the limit inside. And then this just becomes a constant here. It's the limit as n approaches infinity of 1 plus 1 over n to the n. Does anyone recognize that limit? You've seen that before? I'm going to help you out here. Just running through these markers here. 1 plus 1/10, 10, approximately 2.597. 1 plus 1 over 100, 100 is 2.7048. Plus 1,000, 2.7169. And 1 over 10,000 to 10,000. Is 2.71814. See where this is going? This is E. This is Euler's constant. So if we compute interest continuously, as if, we divide time up into an infinite number of pieces, the future value is E times E to the RT. So that's our equation for finding compound interest continuous. All right, so at that point, the example is so let down. So you invest $5,000 at 2% interest for 3 years. Compounding continuously, what is your future value? Will be equal to E to the RT. E is 5,000. R is 2 over 100, 2%. E is, I looked at E, didn't I? That's approximately what? Again, just perfect problem for your TI calculator. 5,309.18 cents. How long until you have $1 million? Well, T, 1,000,000, equals 5,000 E to the 2 over 100 T in years. So again, you can solve for T. Divide through by 5,000. Find the natural log of this, and then divide by 2 over 100. Because I'm curious. Gonna eat into your time. No. Anybody have a calculator with batteries that work? The students have an incentive to get the answer. How many years?
0.18.
Can't be.
I got 264
264 years. So stash that money away right after class and figure out how you're going to live 260 years. Thank you. Have a nice afternoon. Quick comment. I'm going to go down to my office hours. On the first, my office hours will be cut short because I'm in a proctor exam. If that's an issue, let me differentiate T over C or C plus tangent?
No.
Oh, sine of
You did?
No.
Yeah, T sine T over 1 plus T. Yeah.
So we have to use the quotient rule. So the derivative of T sine of T minus 1 plus T. No. Times 1 plus T minus T sine. Have a good day. Times the derivative of 1 plus T, which is just 1. So I'll just put it like this. Over 1 plus T squared. Okay? So the only thing left is T sine of T. They have to use the product rule. So the product rule says T sine of T is T times the derivative of sine of T, T cosine of T, plus sine of T times the derivative of T, which is 1. So we get okay. Now, can we reduce that any? I don't think so. I mean, maybe T sine of T will go away. Yeah. The T sine of T here. If you coil this,
Can on top, the one right before that, can you cancel out 1T over 1T squared? Like, and then have just one?
no, because this
Oh.
doesn't have a factor of
Right,
1
right.
plus T.
Okay, sorry. And you said that T, the bottom, if you got a division, it's T something, what's that?
T cosine T. Derivative of T times the sine of T is the product rule. So T times the derivative of the sine, that's T cosine.
Oh, right.
Sine times the derivative of T. Well, that's 1, so just sine of T.